Section 11.1, Sequences and Series. So what's a sequence? In some sense, a sequence is an infinite list of numbers. The numbers in the sequence are often written as a sub 1, a sub 2, a sub 3, and so on, and the dots mean that the list continues forever. So we're thinking here about sequences as being an infinite list of numbers. So every term has a succeeding one, okay? And for sequences, you can, so it's a list of numbers, so you can order them, right? You can rank them. First term, second term, and so on. For instance, look at this list, 5, 10, 15, 20, 25, and so on. You can think about this as being the first term, so I can label it as a sub 1, the second term being a sub 2, and so on and so forth. We can describe the pattern of the sequence displayed above by the following formula. An is 5 times n. Why? Because, so what's n? N is the rank of the term, right? So the first term when n is 1 is 5 times 1. So a sub 1 is 5 times 1, which is 5. Correct? And what's the fourth term? This is when n is 4. A sub 4 is equal to 5 times 4, which is 20. So it's right there. Correct? What's the 10th term? The 10th term, which comes in the sequence 5 terms later than A5. So the 10th term is when n is 10. A sub 10 is 5 times 10, right? You replace, that's the same n here and here. So whatever you replace here, you're going to replace it here. So a sub 10, which is the 10th term of the sequence, is 5 times 10, which is 50. Okay? You can also think about the sequence as being described, or you can describe it as follows. You can go from one number to the next by adding 5, right? So you can go from one number to the next by just adding 5. Correct? So these are the multiples of 5. That's what we're saying. So every term is going to be 5 more than the previous one. Okay? So another way to represent that sequence can be represented by the following recursive formula or recurrence formula, like this. Every term, so the nth term, is equal to the previous one. So the previous one, if the term is n, has rank n, the previous one is going to have rank n minus 1. So you go to the previous term and you add 5 to get the nth term, the term in the sequence whose rank is n. Correct? So one more time, what does this mean? This means that the term in the sequence whose rank is n is equal to the previous term, so the term who has rank n minus 1, plus 5. Correct? If you follow this recipe, every term is 5 units more than the previous one. Correct? Okay? But this is, I mean, that recursive formula is described based on the previous one, so you have to define the very first term for the user in some sense, and the very first term is 5, right? So A1 would be 5. Okay? So if A1 is 5, what's A2 according to this recipe? Well, we said the second term, so the term who has rank 2, is equal to the previous term. So when the previous term, if we're talking about the second term, we're talking here about the previous term. So this is the first term, and the first term is given to us as being 5. So this becomes 5 plus 5. So a sub 2 would be 5 plus 5, which is 10. Correct? So now we know what a sub 2 is. Now we move on to the next one. So now we replace n by 3. A sub 3 would be equal to a sub 3 minus 1, which is 2, so the second term, plus 5. So a sub 3 would be a sub 2 plus 5, and a sub 2, the second term, is 10, right? 10 plus 5 is 15, so the third term, a sub 3, is equal to 15. Okay? So this is a recursive formula or recurrence formula, so it's given based on the previous term. This, in this context, it can be given based on earlier terms. It doesn't have to be the previous one. All right. So in this section, we're gonna see how these different ways of representing um, sequences are used. Okay. All right. So here's the formal definition of a sequence. A sequence is a function f whose domain is the set of all natural numbers. And what's the set of natural numbers? It's the set of all positive integers, right? So 1, 2, 3, 4, 5, and so on. All right, so a sequence is a function whose domain is the set of natural numbers, and the terms of the sequence, a sub 1, a sub 2, a sub 3, etc., are the function values, f of 1, f of 2, f of 3, and so on. So you can think about the terms of the sequence as the images or the function values that the function can take when the inputs are those natural numbers. So the first term, you can think about it as f of 1, the second term as f of 2, and so on. But typically people do not write, for sequences, they don't write the terms as the images of these natural numbers. They just rewrite them as a sub 1, a sub 2, and so on. So an is the most general term of the sequence. So an is fn, okay, which means a1 is f1, a2 is f2. This is a notation. All right. So a sequence is not too far from the concepts that we learned before. It's actually a function, but the function which operates only on natural numbers. Okay, and the terms of the sequence are the function values that the function can take when the inputs are the natural numbers. Very good. All right, so these a1 is called the first term, a2 is the second term, and in general, an is the nth term. Here's a simple example of a sequence: 2, 4, 6, 8, 10, and so on. These are obviously multiple of 2. So we can write a sequence in this way when it's clear what the subsequent terms of the sequence are. For example, here we understand, those dots means that the pattern is assumed to continue. So the next one would be the next multiple of 2, right? Which is 12, and so on. Okay, so you can start enumerating the elements of the sequence and put ... which means, okay, so I understand now what the pattern is, or the reader can understand it, so they can describe all the sequence. Okay. All right. To be more precise, however, we need to specify a procedure for finding all the terms of the sequence. So if you want to be more precise, you have to find a recipe for the most general term. For example, what's the nth term, right? In this context, what's the nth term, which is an? Well, if the first one is 2, the second is 4, the third is 6, and so on, what's the nth term? Well, it looks like each one, right? Each term is twice that rank. For example, the first one is 2 times 1. The second term is 2 times 2, because this is the second term, right? So first term is 2 times 1, second term is 2 times 2, third term is 2 times 3, fourth term is 2 times 4, fifth term is 2 times 5, and so on and so forth. So the nth term is going to be 2 times n. So that's going to give you a recipe for any term in the sequence. So, and you can read it as follows: the nth term is 2 times n. Okay, so you get this list here. All right. Now, if you want to go back, if you just given this and you want to list the elements, you can take n to be 1, right? The first term, and then replace n by 1. This means a sub 1 is 2 times 1, so 2. I wrote them here. If you want to go to the second term, a sub 2, this means n is 2, so 2 times 2 is going to be 4. The green part is the index, right? The green part is the index. So that guy n is the same thing as the index. So this is the recipe. If you're given this recipe, my point is, if you would like to actually list the elements of the sequence, you can check by hand each one. When n is 1, replace n by 1, you get a sub 1 equals 2 times 1, and so on, right? And if you want to go for the 103rd term of the sequence, you're going to go for n equals 103. So if n is 103, you're talking about a sub 103, which is twice 103, so 206. Okay. All right, here's an example. Find the first 5 terms and the 100th term of the sequence defined by each formula. Let's do a couple of these. How about we go for the second one? So we have that Cn is equal to n squared minus 1. Here they're calling the terms Cn's. So the nth term is called Cn. You can call the nth term as An, you can call it Tn, Rn, Yn, and so on and so forth. So they gave it the name Cn. So the first term is C1, right? The second term is C2, and so on. So this is the general term, the nth term, Cn, and this is for any n, for any natural number n, right? For any natural number n. Correct? Alright, so let's start. So what's the first term? The first term is when n is 1. When n is 1, what happens? Well, see, I'm replacing n by 1. That means this is 1 squared minus 1. Correct? Let me be very clear here. So this is the one that I'm replacing it as, that's the n part, right? That's the index. That's the rank of the term. Okay? So when n is 1, go to the recipe. That's the general recipe for any term. Well, the first term is when n is 1. That becomes the square of 1 minus 1. So that's 0. Okay? Alright. So the sequence first term is 0. The second term, that's when n is 2, correct? Well, when n is 2, you square that n, so C2, you square that n, which is 2, minus 1, correct? One more time, let me be very, very clear here. So that's the index, that's the rank of the term. It's right there. It's right there, right? Correct? Okay, so what's the second term then? Okay, so this is 2 squared, so 4. 4 minus 1 is 3. Okay. How about the third term? N equals 3. So that's going to be C3, right? Okay, that's going to be the square of 3 minus 1. Okay, let's stay with the same level of details. So let's color this part. That's the n, that's the n, and that's the n, right? According to this recipe, that n and this guy are the same. So whichever takes place here is going to also sit here. And that's what I'm doing. Alright, so what's the third term then? What's the third term? 3 squared minus 1 is 8. Correct? And how many they want us to find? They want us to find the first 5 terms. So we still have 2 to go. So let n equals 4 now. Because we found the first 3. Now we're going to go to 4 and then to 5. So we're going to find C4. And C4 is when n is 4. So the square of 4 minus 1. Right? I don't know if I should color this part, but let's do it. Why not? So that's the n part. That's the n part, right? And this is simply 15. Am I correct? 4 squared is 16. And minus 1 is 15. So the third term, the fourth term is 15. How about the fifth term? So this is when n is 5, right? When n is 5 now. Well, that's going to be C5. And C5, according to this recipe still, because that's my recipe to generate all the terms. It's the square of 5. So it's the square of my 5 right? So it's the square of my 5 minus 1. Why minus 1? Because that's the recipe, minus 1. Okay? And what's 25? What's 5 squared? 25. 25 minus 1 is 24. Okay? Alright, and I think we answered this part of the question, the first 5 terms, and they want us as well to go to the 100th term. Since they gave us the recipe of any term, I can go immediately to the 100th term immediately by just replacing n by 100. So when n is 100, C100, that's the 100th term, right? C100 is, according to the recipe still, square that 100 minus 1. Okay? Make sense? So that's got this guy. And that's the same n, correct? And that's equal to 10,000 minus 1, which is 9,999, correct? Doesn't matter, but what's important is how to find it. All right, so what are the terms of the sequence then? How about we color them? So the sequence terms are 0, that's the first term, 3, 9, 8, 15, 24, and so on, and the 100th term is going to be this guy, correct? So if you want to list them, you could put them 0, comma 3, comma 8, and so on, and you're enumerating all, as such, you would be enumerating all the elements, or the first 5 terms of the sequence, and the 100th term, okay? So what I mean is this. You can say, okay, I have 0, 3, 8, 15, 24, dot, 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 and then I'm gonna have this guy as the 100th term, right? Okay. All right. Let's do the fourth one. Still in this example, example 1. Rn is minus 1 to power n divided by 2 to power n. So that's part 2. So we have Rn is equal to minus 1 to power n divided by 2 to power n, right? So we need to find the first 5 terms. How about we find just a couple, or how about we find 3? So the first one, when n is 1, I'm not gonna color code it at this point because we understand how this thing goes. So when n is 1, it's gonna be r sub 1, that's the first term, right? R sub 1, and this is when n is 1, so minus 1 to power 1 upstairs divided by 2 to power 1, correct? So again, I'm following this recipe. This recipe is given for us, the understanding is this is for any natural number n, right? For any natural number n. So it's given for us like this. All right, so I'm going for the first term, which means I'm going when n is 1. When n is 1, this is minus 1 to power 1 divided by 2 to power 1. And what's that? This is minus half. Okay. The second term, when n is 2, R2 is going to be minus 1 squared divided by 2 squared. Am I correct? So what am I doing here? I'm replacing n by 2. I'm replacing n by 2. Now what do I get? I get 1 over 4. Correct? I get 1 over 4. And I hope you start understanding what this minus 1 to power n is doing. It's going to start alternating. The sign of the terms of the sequence. So 1 time is going to be, when n is odd, is going to be negative 1. For example, when n is 1, we got negative 1. And when n is even, that guy is going to be 1, right? So 1 time negative 1, 1 time 1. It's going to start alternate. When n is 3, R3 is So R3 is minus 1 to power 3 divided by 2 to power 3. Do you agree with that? So what have I done? I replaced n by 3 because I'm talking about the third term. Okay? And what do we get here? We got minus 1 cube. And what's minus 1 cube? Is minus 1 divided by 2 cube, which is 8. Okay, so indeed the signs, I mean the sequence is alternating in sign, right? One time negative, one time positive. All right, I'm not gonna go to the fifth one. I'm gonna just answer the 100th term, when n is 100. So when n is 100, I'm gonna still follow the recipe. The 100th term is gonna be minus 1 to power what? To power n, which is 100 in this case, 100. So to power 100 divided by 2 to power 100. Am I correct? And what's minus 1 to power 100? Is 1, because 100 is even, so this is 100. Divide by, don't worry about this, just keep it 2 to power 100, whatever it is. Okay. Alright, so this would be the 100th term. And please complete the rest, just do the fourth and the fifth. And complete this example. Okay. But I hope you got the idea. Example 2. Find the nth term of a sequence whose first several terms are given as such. So now they gave us the terms. In the previous example, they gave us the recipe, right? They gave us the formula of the general term, and we had to discover those first 4 terms, let's say, or 5 terms. In this context, now they gave us the first few terms, and they told us, okay, assume that the pattern keeps going. Give us such a formula. Give us such a formula. Okay, so take a look at one. Obviously, stop the video and try to come up with it on your own. The way I'm gonna approach it, I'm gonna realize that all the numerators are odd and all the denominators are even. That's my first observation. And those even guys downstairs, the first one is 2, which is 2 times 1. The second is 2 times 2. The third is 2 times 3. And the fourth is 2 times 4. And I'm gonna expect the next to be, which is the fifth, to be 2 times 5, right? To be 10. And so on and so forth. Right? Every even number can be written as 2 times n. In this case, for the first guy is twice the rank, 2 times 1, right? Let me write it on the screen. So 2 times 1, which is the rank of that term. That's the first term. So it looks like that's the term. That's the rank. So 2 times 1. This 4 can be thought of as 2 times 2, right? That 4 can be thought of as 2 times 2. And this 2 here is the rank, because that's the second term. And this guy is going to be, the guy downstairs is 2 times 3, right? 2 times 3. And that's 3 again. It's the rank of the term. And so on and so forth. So it looks like the nth term, the guy downstairs is going to be 2 times n. That's how it looks. Make sense? Because as we discussed, the first guy looks like 2 times 1. The second guy looks like 2 times 2. So this 2 being the second term. 3. 2 times 3 as being for the denominator of the third term. For the fourth term, the denominator of the fourth term is going to be 2 times 4. The denominator of the fifth term is going to be 2 times 5. The denominator of the nth term is going to be 2 times n. Okay? N being the rank of the term. Okay? Very good. How about the numerator? Well, all the numerators here look like, if you take a look at the numerators, they are odd, as we said, but moreover, they are 1 unit less than the denominator, right? Because, every odd differ from an even number by 1, right? So either you increase it by 1 or you decrease it by 1. In this case, I'm gonna decrease that guy downstairs by 1 because every numerator is 1 less than the denominator, correct? So who's gonna sit here then? That's the 2n minus 1. Do you agree with that? So it's 2n minus 1. This is a recipe, and if you want to simplify this, sure, you can write it as 1 minus 1 over 2n, right? So if you want to simplify this, you can still simplify it, but you don't need to. 2n minus 1 is the same as 2n over 2n, which is 1, minus 1 over 2n, which is 1 over 2n, correct? This step is not necessary. This is correct. Part 2. Here I have minus 2 as a first term, 4 as a second, minus 8, 16, and so on. It looks like the signs are alternating, and we just learned what factor makes that sign alternate. It's minus 1 to power n, correct? So if you look at the nth term as being minus 1 to power n times something, I still have to figure out that thing. But look, if n is 1, so I'm talking about the first term, if n is 1, that's minus 1 to power 1, which is minus, so it looks good. When n is 2, that's minus 1 to power 2, so it's 1, so it's plus. So when the rank is odd, as you see here, minus 2, minus 8, minus 5, minus 32, have odd ranks. This is the first term, third, fifth. They have a sign negative, so that can be represented by this. And now the even ones, the even ranked, so the second, the fourth, they have positive signs. So as such, if you raise this guy, if n is even, that guy is gonna be positive 1. Okay, so the sign part looks good. Now let's look at the numbers. They look to me very much as powers of 2, right? This is 2 to power 1, this is 2 to power 2, this is 2 to power 3. I'm ignoring the sign. I took care of the sign, right? I'm trying to answer this question mark. Who should be here? Well, again, as we said, this looks like, all these guys look like powers of 2. So this is the first power of 2. So for the first term, this is the first power of 2. For the second term, this is the second power of 2. For the third term, the third power of 2, and so on. For the fifth term is the fifth power of 2, right? 2 to power 5 is 32. And for the nth term is going to be what? It's going to be the nth power of 2. And what does this mean? It means 2 to power n. Makes sense? This is 2 to power n. Upstairs it was 2 times n. That's different, right? Different. All right. So we got this. All right. So this would be, what is it? So we answered the question. The nth term of the sequence is given by this formula, right? Okay. Let me go to the next page. So as we said, as we said before, some sequences are given by the recursive formula or the recurrence formula. Here's an example. Find the first 5 terms of the sequence defined recursively by A1 is 1, so the first term is 1, and the nth term is 3 times the entity, the quantity, the previous term, the n minus 1th term, or n minus 1st term, plus 2. Okay? So what do they want? They want us to find the first 5 terms of the sequence. So how about we find, they gave us the first one. They gave us A1 equals 1. How about we find the second now? Well, the second, A2, let me change the color. This is close to that. How about purple? A2, which is the second term. Well, the second term, what am I choosing for n? What am I choosing for n? 2, right? Because I'm talking about the second term. If this guy is 2, that's gonna be 2 here, right? And hence, what's this piece? What's 2 minus 1? Isn't it 1? So this whole thing becomes a sub 1, right? This whole thing becomes a sub 1. right? So a sub 2 is what? A sub 2 is 3 times the quantity a1 plus 2. And how much is a1? They gave it to us. This is 1. Make sense? So a2 is 3 times a1 plus 2. But a1, we know it's 1, right? And 1 plus 2 is 3. 3 times 3 is 9. Make sense? So this is how we find the second term. Let's keep going. Now this third term, they want the first 5. Let's find all of them. So the third term, this is when n is 3. So I want to find a sub 3 now. This is when n is 3, right? When n is 3, that's going to be 3 here. So 3 minus 1 is 2, correct? 3 minus 1 is 2. So this becomes a sub 2 then. And how much is a sub 2? We found it to be 9. So how much is this? That guy is 9. So this becomes 3 times a sub 2 plus 2. Okay, and a sub 2, the second term is 9, as we found before. 9 plus 2, how much? 9 plus 2 is 11, and 11 times 3 is 33. So the third term is 33. Okay, all right, on to the second, the next term, which is the fourth term. And now I'm talking about n being 4. And if n is 4, that index here, which is n minus 1, that's going to be 3, right? So the whole thing becomes the third term, a sub 3. Okay. So a4, the fourth term then, is 3 times a3 plus 2. And how much is a3? 33. So a sub 3, we found it to be 33. So 33 plus 2, 33 plus 2 is 35. And 35 times 3, so 35 times 2 is, what is it, 70, 70 plus another 35 is 105, right? Okay, so this is the fourth term. And the last term now, this is when n is 5 this time. When n is 5, so when n is 5, this is going to be 3 times the quantity a4 plus 2, right? And what's a4? It's 105. So that's going to be 3 times 105 plus 2. All right, so you find this. But you got the concept, hopefully. So given that recursive formula, I can start establishing the sequence, the terms of the sequence, right? So which means that a recursive formula is enough, is sufficient to actually describe the entire sequence. Make sense? All right. The next one, the Fibonacci sequence. This is after the Italian mathematician who discovered the sequence. He wasn't the first one actually to discover this. Let me tell you this. There was an Indian poet who actually discovered it before, but he was too far to publish it in the West. So Fibonacci actually published it before. Anyway, so he's an Italian mathematician who lived in the 13th century, and he used the sequence that we're about to talk about. He used it actually to solve a problem about the breeding of rabbits. Okay. All right, so what's the sequence? It's given by the following recursive formula. F1 is 1, so F for Fibonacci. So the first term is 1, the second term is 1, and in general, the nth term is the sum of the two preceding ones, right? This is what this is. So the nth term is the n minus first term, which is the previous one, plus the n minus second term, which means the previous to the previous, so two terms before the nth term, right? So long story short, each term is the sum of the two preceding ones. Make sense? This is what this recipe is saying. This is for any natural number bigger than 2, which means it starts at 3. right? What's the first natural number after 2? It's 3, right? So this is when n is 3, this is where it starts. And what's f3? Because they want us to find the first 11 terms, okay? They give us the first 2. Let's find the rest. Let's find the rest. How about I cram it here? So how about we find the third, f3? Well, f3, as we said, it's the sum of the preceding 2 terms, so f3 is going to be the sum of the first 2 terms then. So 1 plus 1, right? So f3 is f1 plus f2, correct? Which means, to stay with the same writing, I should write f2 plus f1. Why? Because here I'm taking n to be 3. If n is 3, this thing becomes 2 here, so it becomes f2, right? f2. And if n is 3, that becomes 1, so this becomes f sub 1. Make sense? Alright, so we get this, and this is equal to what? 1 plus 1, just 2. So the third term is 2. How about the fourth term? I'm not gonna go and find the first 11, to be honest. I'm gonna just find a few. How about the fourth term? It's gonna be the sum of the 2 preceding ones, which are the third and the second term, right? Because what are the 2 preceding ones to 4? They are the third and the second. Now how much is this third? It's 2. How much is the second? It's 1, right? So that's gonna be 3. So far the sequence looks like this: 1, 1, 2, 3, and hopefully you can continue the rest. What's the fifth? It's the sum of the fourth and the third, right? These would be the 2 preceding ones. What's the fourth? It's 3. And what's the third? It's 2. So it becomes 3 plus 2. And what's 3 plus 2? It's 5, right? So the next one, I'm gonna write one more, f7. So sorry, f6, which is the 6th term. It's gonna be the sum of the 2 preceding ones, which are f5 and f4, the 5th and the 4th, right? And how much is f5? f5 is 5, and f4 is 3. So the 6th term of the sequence is 8. So far, how does the sequence, how is it shaping up? It's shaping up like this. First term is 1, 1, second is 1, 2 as being the third, 3 as being the fourth, 5 as being the fifth, and 6 as being, or 8 as being the 6th. Correct? And so on and so forth. What's the next one? The next one is going to be the 7th term, and according to this recursive formula, it's going to be the sum of the 6th term, which is 8, and the 5th term, which is 5. And 8 plus 5 is 13, so f7 is going to be 13, and so on and so forth. Okay? Alright. Next concept. So it says here in calculus, we are often interested in adding the terms of a sequence. So if you have a sequence like this, a1, a2, a3, and so on, we are often interested to add up these guys. And in order to add them up, you're gonna define what people refer to as partial sums. And what's a partial sum? Here's the definition. So given a sequence as described above, the first partial sum, right? The first partial sum, which is denoted here by s sub 1, it's gonna be just the first term. The second partial sum, s2, is gonna be the sum of the first 2 terms, a1 plus a2. So again, we are defining the sequence, right, of partial sums. So each one of these is referred to as a partial sum. This is the first partial sum, second partial sum, and so on. So again, what's the first partial sum? It's just the first term. What's the second partial sum? That's the first of the sum. It's the sum of the first two terms. What's the third partial sum, S sub 3, is the sum of the first three terms. Okay, that's the definition. So in general, what's the nth partial sum, S sub n being the nth partial sum? It's gonna be the sum of the first n terms of the sequence. Make sense? Okay, and those the terminology I just used here is here. Okay. All right. So and the sequence at the end of the day, S1, S2, S3, all these guys. If you just focus on the left side, S1, S2, S3, S4, etc., all the way to Sn, and that thing keeps going. That's the sequence of partial sums. Okay, because each term in this sequence, is a partial sum itself. Okay. All right. So how can we summarize this again? The definition: you have a sequence A1, A2, A3, A4. You can associate to this another sequence, and that sequence has terms, each of which is the sum of the first few terms. For example, the nth term in this sequence, in this new sequence, the partial sum sequence, the nth term of that is the sum of the first n terms of the AI sequence. Okay? All right. Example 5. Find the first four partial sums and the nth partial sum of the sequence given by a sub n equals 1 over 2n. You know what I'm gonna do? I'm gonna just include something here. I'm gonna say and guess. We learn how to actually find the exact value of that nth partial sum in the future or in a future section. I'm gonna just say here, make an educated guess about the nth partial sum of the sequence an equals 1 over 2n. Okay. All right, so let's talk about this. Let me take this example to this blank page here. So this is example 5, and it goes like this. What do we have? We have an is equal to 1 over 2 to power n, and this is for all natural numbers n, right? For all natural numbers n, right? Okay. So what does it mean? It means that when n is 1, I have 1/2. Correct? When n is 2, I have 1 over 2 squared, which is 1/4. Agree with me? And when n is 3, I'm gonna have 1 over 2 cubed. And 2 cubed is 8. And so on. Okay? The question is, what's the question again? The question is to find the first four partial sums. All right, let's find the first four partial sums. What's the first partial sum? It's denoted by S sub 1, and according to the definition, S sub 1 is just the first term. It's the sum of just the first term, so which is itself. So it's A1. And what's A1? It's half, right? Okay. S2 is equal to the sum of the first two terms, so A1 plus A2. This is the definition. Here it's just definition. I'm not using anything, right? The first equality here is definition. And what's A1 plus A2? What's A1? A1 is half. And what's A2? A2 is 1 over 4, right? 1 over 4. And what's this guy? What's 1/2 plus 1 over 4? This is 3 over 4. Am I correct? Okay. All right. What's the third partial sum? What's the third partial sum? Well, the third partial sum is A1 plus A2 plus A3. Why? That's the definition again. I'm not doing anything. I'm just applying the definition. Which definition is it? It's right there. The definition of partial sums. S3 is A1 plus A2 plus A3. Okay. So I need to find A1, A2, and A3. They are here. 1/2 for A1. 1/2 for A1. For A2, how much is A2? We found it to be 1/4. And for A3 is 1/8. You agree with that? Now how much is this? If you do the same denominator, which is 8, that's gonna be, I'm multiplying here by 4, so that's gonna be 4 plus, here I multiplied by 2, so 4 plus 2, which is 6 plus 1, that's gonna be 7. Make sense? Okay. And S4, it's gonna be the sum of the first 4 terms, so A1 plus A2 plus A3 plus A4. Agree with that? Okay. And if you add them up, well, what's A1 first? A1 is half. A2 is 1/4. We found them before. A3 is, what is it? 1/8. A4, we didn't write A4, but it's not hard to be found. A4 is 1/2 to the power 4, right? A4 is 1/2 to the power 4, and what's 2 to the power 4? 16. So plus 1/16, correct? And if you write the same denominator here, which is 16, so that's gonna be times 8. So 8 plus 4, that's 12. 12 plus 2, that's 14. Plus 1, that's 15. 15/16. Okay. So what's the sequence of partial sums then? It looks like the sequence of partial sums is gonna be 1/2, 3/4, 7/8, 15/16. These are the first 4 terms in the sequence of partial sums, right? Remember, SI is the ith partial sum, and they can form a sequence, right? S1 is 1/2, S2 is 3/4, and so on. I can keep going. Sn is going to be the sum of the first n terms. You're going to find a value. So the sequence is shaping up as such: 1/2, 3/4, 7/8, 15/16, and so on. And the question is, can you make a guess about the nth partial sum? Can you make a guess about the, if you say here ... can you make an educated guess about the Sn, which is the sum of the first n terms? Well, we just looked at this before. This sequence, it looks like something we've seen a few minutes earlier. I'm alluding to where is it? This sequence here, right? I'm talking about this sequence here. This is S1. This guy is S2, right? These are the guys we just found. S3, S4. You agree with that? So it looks like the nth term, we found it. The nth term of the sequence is gonna be that guy, 1 minus 1/2n. Correct? Remember this discovery that we did a few minutes earlier? So in our context then, because of that problem, which problem was it? Example 2. So because of example 2, I can make the following guess, that the nth term of the sequence of partial sums, so the nth partial sum, so if you add up the first n terms in this sequence, so if you add up a1 plus a2 plus a3 plus all the way to an, this is what the nth partial sum is, right? So again, let me write it for you. So let me save this for later. This is a1 plus a2 plus a3 all the way to an. This is the definition of Sn. And according to example 2, a good guess would be that this is actually 2 to power n minus 1 over 2 to power n, which we simplified it to be 1 minus 1 over 2n. Correct? Again, this is a guess. Why this is for sure correct? You're gonna see it in a future section. Okay? Alright, so the next example, example 6. Question is, find the first 4 partial sums and guess, let's keep the question, guess the nth partial sum of the sequence given by an is equal to 1 over n minus 1 over n plus 1. Okay? Alright, so we're gonna do the same thing as above. For example 6, we have an is equal to 1 over n minus 1 over n plus 1, and this is for any natural number n. Okay? Alright, so the question is to find the first 4 partial sums and make a guess for the nth partial sum. How about we start with the first one, S1. S1 is A1, right, by definition. And A1 is, this is the recipe for any term. For the first term, so for A1, that's 1 over 1, which is 1, minus 1 over 2. Okay? So 1 minus half is S1, which is half, right? Okay, I'm gonna just keep it for this, just for because I wanna try to convince you what the nth partial sum is. You're gonna see. S2. What's S2? It's the sum of the first 2 terms. So it's A1 plus A2. And what's that? What's A1 plus A2? Well, A1 is that thing, we just found it, 1 over 1 minus 1 half, plus A2, A sub 2, the second term. The second term is 1 half minus 1 over, now is n is 2, right? Again, what I'm doing here is I'm replacing, to find A2, I'm replacing n by 2. So that's going to be 2 and that's going to be 2. And let's read it. A sub 2 is 1 half minus 1 over 3, right? So 1 half minus 1 over 3 is that guy. So that's A2 and that's A1. So A1 plus A2 is this. Okay? And now what's this guy? What's 1 minus 1 half plus 1 half minus 1/3? I hope you observe that this guy and this guy are going to cancel each other. And then what do we get? We get 1 minus 1 over 3. Alright. S3, which is the third term now, the third term in the sequence of partial sums. So S3 is the sum of the first 3 terms in the sequence AN, right? So A1 plus A2 plus A3. And that equals to A1, we found it, so that's 1 minus 1 half. A2 is 1 half. Let me fix this 2 here. So 1 minus 1 half plus A2, I'm talking about A2, which is 1 half minus 1/3. And now A3. A3, I'm gonna go to the recipe of the AI. This is what generates all the terms, right? All the AI terms. A3, I'm talking about n being 3. If n is 3, that's gonna be 3, that's gonna be 3. A3 is gonna be 1/3 minus 1/4, right? So 1/3 minus 1/4. Okay. So 1/3 minus 1/4. And how much is this? That half and this half are going to cancel each other. That minus 1/3 and this plus 1/3 are going to cancel each other. How about we keep them the same color? How about green for this? These are going to cancel each other. And then who's going to survive? It's just 1 minus 1/4. So it's just 1 minus 1/4. I hope you start seeing the result. So S1 is 1 minus half, S2 is 1 minus 1/3, S3 is 1 minus 1/4. Can you anticipate what S4 is going to be? Apparently it's going to be 1 minus 1 over that index plus 1, right? 4 is the index plus 1. 3 is the index 2 plus 1. 2 is the index 1 plus 1. So apparently S4 is going to be 1 minus 1 over 5. Let's check. S4, which is the sum of the first 4 terms, so A1 plus A2 plus A3 plus A4. What's A1? Is 1 minus 1/2. A2 is 1/2 minus 1/3. A3 is 1 over 3 minus 1 over 5. And lastly, A4. A4, what's A4? It's 1 over 4 minus 1 over 5, right? 1 over 4 minus 1 over 5. You agree with that? And then if you start subtracting those guys that are the same, or adding, I should say, this and this cancel, this and this cancel, and who survives? As expected, 1 minus 1 over 5. So a good guess would be, a good guess for the nth term, right? For the nth term, the nth partial sum, a good guess would be Sn is 1 minus 1 over n plus 1, right? That would be a good guess. Let me convince you even more. Sn is A1 plus A2 plus A3 plus all the way to the nth term. So the previous one is an minus 1 and then an, right? Well, A1 is 1 minus 1/2. This is A1. A2 is 1/2 minus 1/3, right? This is A2. A3 is 1/3 minus 1/4, and so on, right? What's the n minus first term? What's the n minus first term? I'm gonna replace this guy by n minus 1, okay? So I'm replacing each n by n minus 1. Each n is replaced by n minus 1. And now let's read this. What's a sub n minus 1? It's 1 over n minus 1 minus 1 over n, right? Because minus 1 plus 1 cancel. So what's a sub n minus 1? Let me write it here and then copy it. So what's a sub n minus 1? What's written in brown here? 1 over n minus 1 minus 1 over n, right? Because if you replace n by minus 1 by n minus 1, you get n downstairs. You agree with that? So I'm gonna take this and take it with me down to the discussion below. All right, let me erase these guys. All right, so down here. So now I'm gonna paste the n minus first term. So I'm gonna paste it right here. So this is the n minus first term, right? So this is the n minus first term. And then what's the last term? What's the last term, which is the last term in this nth partial sum, which is an. What's an? Is 1 over n minus 1 over n plus 1, right? It's 1 over n minus 1 over n plus 1. Agree with this? Okay, so look at this sum. Look at this sum. The negative half is gonna cancel the half. The negative 1/3 is gonna cancel the plus 1/3. So apparently the negative part is coming before the positive part, right? The negative half canceled the half because the negative half came before the half and then they cancel. The negative 1/3 came before the 1/3. The negative 1/4 is gonna come before the 1/4. So the next one is gonna be 1/4. Do you agree with that? The next one is going to be 1/4. That one is going to cancel this one. And all of these are going to start collapsing each other. They're going to cancel each other. And as we said, the negative one comes before the positive one, right? The negative one comes before the positive one. Here I have positive 1 over n minus 1. So somewhere before, actually the one before actually canceled it, or the minus occurred right before that. So the minus 1 over n minus 1 came before that positive 1 over n minus 1. So they cancel each other. This guy, the negative 1 over n, its positive part is going to come after. And it comes immediately after. It's right there. And then this guy doesn't have any partner because the guy that's going to cancel it comes after. Remember, the negative comes before the positive according to the sum here. So the first one, or the positive part, comes after, but we already stopped. So this guy doesn't have a partner. So what's going to happen is this is 1 minus 1 over n plus 1. Correct? So this is more than being a guess at this point. It's just, it's the truth, right? It's the truth. This sum is said to be a telescoping sum because as you see, it collapses like the pirate's telescope. Okay. All right. So anyway, so Sn is 1 minus 1 over n plus 1 as expected. S4 was 1 minus 1 over 5, so that guy is 4 plus 1, right? So n plus 1 in this case would be 5. 4 here is 3 plus 1, correct? And so on and so forth. So this is what the nth partial sum looks like. Okay. So we're done with 6. We made more than a guess in this case, right? All right, so the sigma notation. What's sigma notation? Given a sequence A1, A2, A3, all the way to A4, all the way to AN and ... we can write the sum of the first n terms. We know that the sum of the first n terms, the name is the nth partial sum, right? But we can write it using the summation notation or the sigma notation, using that Greek letter sigma. This is capital sigma, okay, corresponding to our S in English, right? And the sigma notation is used as follows. This is the notation. This is the definition of it, okay? Sigma AK, K goes from 1 to n, means it's the sum of the first n terms. So it's the sum of the terms A1, A2, A3, and so on. Correct? So again, this is a sigma. It's a sum of all the terms that look like A sub k. Each term here looks like A sub k, right? And this guy k, this index k, ranges from 1 all the way to n, right? It goes from 1, 2, 3, all the way to n. Make sense? So this is the sigma notation. All right, let's keep going. The left side of this expression is read as the sum of AK from k equals 1 to k equals n. The letter k is called the index of the summation, or the summation variable, and the idea is to replace k in the expression after the sigma by the integers 1 through n, and add the resulting expressions arriving at the right-hand side of the equation. Okay, so this discussion we just made above. The sigma notation is simply a compact way to represent a sum. Okay, so just think about it as a compact way to represent a sum. Look at this. Example 7. Find each sum. So find the sum. Summation of these 5 terms, where each term looks like k squared and k ranges from 1 to 5. What does this mean? What does this mean? Well, this means when k is 1, this becomes 1 squared. k is gonna go from 1 all the way to 5, right? So when k is 1, I get 1 squared. I'm adding, sigma means I'm adding, so add. When k now move to the next one, which is 2, it becomes 2 squared, correct? And when k now moves to the even next one, so after 2 comes 3, so 3 squared, correct? And I'm getting closer to 5. I still have to go to 4. 4 squared is the second to last, and then the last one is 5 squared, correct? So this would be the sum. Obviously you can find it. What's the sum? I'll let you figure that out. Okay, let me just clean it a little bit. So just add it up. So 1 squared, just 1, plus 2 squared, so 4, 3 squared is 9, 16, 25. Just add it up and you find that this sum represents this number, whatever this number is. Okay, so I hope you see that this is a compact way of writing this. And if k is like 100, if k can go all the way to 100, this becomes way longer, and obviously you start seeing the benefit of this representation. Okay, let's do part 2. Let's do part 2 here. So part 2, we're gonna add the terms that look like 1 over j, and j ranges from 3 to 5. So this is equal to, let me change the color. So this is equal to, j starts at 3 this time, right? So the least it can get is to 3. So the first term in this summation, the first summand, is 1 over 3, correct? And then after 3 comes 4, so I'm headed towards 5, right? So when the index is at 3, I get the term 1 over j is 1 over 3. When j is the next one, which is 4, that becomes 1 over 4. And then the very last one is to the 5, so the term becomes, now the index is at 5, j is 5, so this summand becomes 1 over 5. Okay, again, I'll let you figure out the sum. Let's go for the last one, 5. For 5, I'm gonna add the terms. Okay, look at this. I'm adding the terms. Each of the terms looks like just 2, a pure constant 2. So I'm gonna add the terms, all of which look like 2. I'm gonna add 6 copies of that. Okay, so let me put it in perspective. Take this guy as being AI, right? So this is AI. No matter what I is, AI is 2. This is what this says, right? So no matter what AI is, no matter what I is, AI is 2. Okay, so what does this mean? This means then that this is equal to, let me just close that here. So this is equal to A1, right, plus A2 plus A3. I'm adding those AIs, right? I mean, ignore this, just pretend that this is masked or something, okay? Ignore that. It's AI. So sigma AI, where I ranges from 1 to 6, means A1 plus A2 plus A3 plus A4 plus A5 plus A6. Doesn't that, the notation sigma I from 1 to 6 AI, doesn't that mean this when we ignore this guy 2 and we replace it by AI? Okay, so this is just by definition by notation. And now what's A1? Well, A1 is 2, no matter what I is. As you see, the result here has nothing to do with the I. So A1 is 2. Each AI is 2. So this is 2, this is 2, this is 2, and so on. All of these are 2. So what does this mean? This means I have 2 plus 2 6 times. Does this make sense? So one more time. I replaced this guy by AI just to put it in perspective, to go back to the definition. This becomes sigma as I ranges from 1 to 6 of the terms that look like AI. Well, this means A1 plus A2 plus A3 plus all the way to A6. Okay? And now, what is each AI? Well, A1 is 2. A2 is also 2. A3 is also 2, and so on. So I have 6 2's. Alright, and this is 12, right? Make sense? Okay. I'll say this orally. What does this mean? So I'm adding terms that look like, each term looks like I, and I ranges from 5 to 10. So what does it mean? What's the first term? The first term is when I is 5, so the first term is 5. The second term is when I is 6, so the second term is 6. So this becomes 5 plus 6, and you keep going. Plus 7, plus 8, plus 9, plus 10. So this is what this sum is. It's the sum of the terms from 5 to 10. This is what this means. Okay. Alright, so example 8. Write each sum using sigma notation. So we're gonna take a look at this. So they gave, now it's backwards, right? So they gave us this writing, and we wanna write it in a compact way. We wanna write using the notation, the sigma notation. What's this guy here? Each term looks like something to power 3, correct? Something to power 3. And that thing is ranging from 1 to 7, right? So this guy, look, each term, it's a summation, each term looks like something to power 3, right? Each term looks like something to power 3. And that thing is a guy, call it K, that's ranging from 1 to 7. Do you agree with me? So this is a way to represent this. Now, I mean, go back if you wish. Try to write it backwards, or just to convince yourself even more. When k is 1, this becomes 1 cubed, first term. When k is 2, this becomes 2 cubed, and so on and so forth. And the last term is when k is 7, you get 7 cubed, correct? Okay. How about part B? How about part B? So this looks like, this is a summation for sure of the square root of something, right? And each guy here is a number that's between 3 and 77. It's a natural number that's between 3 and 77, correct? So it's a summation of terms that look like sigma, that looks like square root of k, where k goes from 3 all the way to 77. Make sense? So that radicand ranges from 3 all the way to 77. Okay. There's another way to represent this. There's another way to represent this. What's that way? Look, this is correct now, okay, no doubt. I'm gonna just show you a different way to write it. How about we do the following substitution? How about we call m? How about we call m to be k minus 3? Okay. How about we call m to be k minus 3? Let's rewrite this now in terms of m. I'm doing this substitution. We're gonna see why just in a second. It's not crucial, it's not important, but it's just for you to be able to see that when you write a sum, it doesn't have to be a unique way to write it. Okay, there are multiple ways to write a sum. I'm trying to write it in a different way. Okay, so replace, every time you see k minus 3, replace it by m. In other words, m plus 3 is k, right? Solve for k here, you get k equals m plus 3, correct? All right, let's write this summation with this substitution. So we get sigma, right? Sigma square root of what? What's k in terms of our new notation here, new parameter. Instead of k, now we're gonna have an m. But what's k in terms of m? It's m plus 3, right? So k is m plus 3. So instead of k, I'm gonna write m plus 3. Agree with that? And now, if k goes from 3 to 77, where does m ranges? Where does m range? Again, if k goes from 3 to 77, m ranges from what to what? What's the lowest value that m can start from? Well, if k's lowest value is 3, m lowest value is gonna be 3 minus 3, so 0, right? And what's the highest value for m? Well, if the highest value for k was 77, the highest value for m is going to be 77 minus 3. So the highest value of m is going to be the highest value of k minus 3. So 77 minus 3 is 74, right? That's 74. Okay. To convince you, or to convince yourself, how about you actually ignore that writing and just try to unravel what this means. This means summation of terms that look like sigma m plus 3, and m goes from 0 to 74. What's the first term here? When m is 0. When m is 0, I get square root of 0 plus 3. And what's square root of 0 plus 3? Square root of 3. So we get back this. What's the next term? When m is 1. Remember, m goes from 0 to 74 with an increment of 1 each time, right? It's just visiting all the integers from 0 to 74. When m is the next one, so when m is 1, that becomes square root of 1 plus 3, which is square root of 4. Correct? And even the next one, when m is 2, I'm going to have square root of 2 plus 3. 2 plus 3 is 5, so I get this. And what's the highest m can reach? Is 74. When m is 74, this becomes square root of 77, so it's correct. So these guys are the same. These guys are the same. So when you write a sum of terms, it doesn't have to be a unique way to write it. There are multiple ways. How about I ask you this question and you think about it on your own? Can you rewrite this as sigma? Let's choose a different letter. How about P? That starts at 1 instead of 0 and instead of 3, and ends, where should this end? And what should be the term? Can you complete this? Can you complete this? Can you make, do you see what P should be in terms of n? Think about it. All right. And finally, the following properties of sums are natural consequences of properties of the real numbers. So let me take you to that page. All right, so these properties are as follows. Here's the setup. You're gonna have two sequences, the AI sequence and the BI sequence. So you have two sequences. The terms of the first sequence looks like AI, right? Each one looks like AI. The second one, each one looks like B sub I. Then for every positive integer n and for any real number c, the following properties hold. The first one says if you add up the terms that look like ak plus bk and you let k range from 1 to n, that's the same thing as taken the sum of the ak's from 1 to n and the sum of the bk's from 1 to n and add up the results. Okay? You can do similar game for differences, and if you have a constant c, you can push it outside as long as this constant doesn't depend on k. You can push it outside. It doesn't depend on k means you don't see the index k in it, right? It's a pure constant. You can push it outside that sigma. And the last one, if you're adding up a pure constant that doesn't depend on k, this is the same thing as adding the same thing k n times, right? So c times n. Let's prove most of them. And let's start by the first one. So let's prove the first one. So what does this mean? Sigma AK plus BK, where K goes from 1 all the way to N. What does this mean? Well, when K is 1, this means A1 plus B1, right? Plus, because I have sigma. When K is 2, this means A2 plus B2. When K is 3, this means what? A3 plus B3. Correct? And so on. And when K is reaching the largest value it can reach, which is N, that's gonna be AN plus BN. Correct? So we get this. And then, are the parentheses doing anything here? They're just grouping. Since addition is associative, I can drop these parentheses, I can group them the way I want, and since addition is commutative, I can reverse the order of any two, right? So at the end of the day, I can write the AI's back to back in order, correct? And I can add that result because of the associativity of addition and commutativity of addition. I can do so and then add this result to the sum of all the BI's when I place them back to back, correct? Again, what's the real engine here is that addition is associative and commutative, right? Remember, associativity has to do with grouping and commutativity has to do with the order, right? So the order when you add doesn't matter if you add A1 plus B1 or B1 plus A1, correct? And the group doesn't matter because of associativity. So we get this. And then what does this mean? What does this mean? Well, this means sigma. This means sigma AI or a K, same thing, it's a dummy letter. So K goes from 1 to N. This is for this guy, correct? Plus, and how about this guy? It's very similar to it, but the terms names are BI now. So BK, K goes from 1 to N, correct? So what did we get? We got exactly what we wanted. We got exactly what we wanted, this one, right? So we showed that this sum, the left side is equal to this guy, which is the right side. The difference is the same, just put minuses here and so on. How about 3? How about 3? Can you prove 3? Alright, how about I'll do it. So let's do 3 together. So for part 3, I have that this summation I want to show that this summation is C times the sigma, right? Okay. Alright, how about we call this guy, how about we give it a name? How about we call this guy X sub K? How about that for a label? Okay, so how about we call this X sub K? Ignore this for the moment, just forget about this. This sigma becomes sigma K goes from 1 to N XK. What does it mean? Well, it means it's x1 plus x2 plus x3 plus x4 plus dot 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 all the way to xn. Yes? Okay. Now, what's x1? Each xk is CAK. What's x1? Well, x1 is CA1. Agree? What's x2? Remember, xk denotes for us CAK. So x2 is going to be CA2. By CA2 I mean C times, right? This is times. This is times. And so on and so forth. This is what's x3? Is C times A3. x4 is C times A4 plus all the way to C times AN. Correct? We get this. Can't you factor out now a C? Can't you factor out this common factor C using the distributive property, right? Using the distributive property. So what goes here is the distributive property. Correct? So meaning you can factor out a C, and this becomes A1 plus A2 plus all the way to AN. Alright, and this is C times this sum can be represented by the sigma notation. So each term looks like a K, and K goes from 1 to N. Correct? Alright, so this takes care of 3. You see? It's right there. This is what we showed. And lastly this, on part 4, we talked about it a couple of times. We talked about it above as well. Correct? C at the time was 2. So this term is a constant independent of the index K. So each term is C. So you're adding C n times, right? You're adding C n times. We talked about this above. So we're adding C n times. As such, what's C plus C, etc. n times? Isn't it Cn? Isn't it Cn? Correct? Alright, so this takes care of this section.